Okay, hello everybody. I'm Federico, and I know you guys had a couple of beers. You talk about random things. So what's better way of finishing up the evening if not to talk about cryptography? So today we're going to talk about zero-knowledge proofs, which are really cool cryptographic tricks. But first, I'm going to talk about myself. So I'm Framp. You can find me with that name everywhere. So if you want to ask me something about this or anything else in particular, just hit me up. I work at TESS. I'm a very passionate learner. Like 5 years ago, I was working in a startup. It was my startup, and I didn't have absolutely time to learn new things. So as soon as the startup finished the money, which always happens, no? I just decided to dedicate a lot of time to learning. So I started looking into functional programming, cryptography, all things that I always thought they were unattainable because you just need to invest a lot of time into it, right? Right now I even work for a company that is very focused on education. I work for TESS, like Marco, and we are a big community of teachers. We are hiring, of course, blah, 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 blah. So anyway, what I want to say is that even if it looks very abstract and it could be scary, it's doable. It's just a matter of spending the time. So I'm sure I didn't scare you at all with this. Zero-knowledge proofs, what are they? So zero-knowledge proofs are a really nice trick, as I was saying. So let's say we have a prover, Peggy, that wants to prove to a verifier, Victor, that she knows a value X. So we want to prove something to someone else. But we don't want to reveal any other information. We don't want to reveal properties of X. We don't want to reveal how we got X. We don't want to reveal anything. Because why would we do that? I mean, come on. It's our business. So is there a way to do that? It depends. So let's take an example. Where is Wally? So Where is Wally? It's a great game. You just have a bunch of, it's a massive drawing, and there are a lot of people with, and somewhere there is a very small man, and you have to find this Wally. So let's say that Peggy managed to find Wally, and she wants to prove Victor that yeah, she did it. Yeah, she finished the game, but she doesn't want to let Victor know that she found the solution. She doesn't want to let Victor know how she found the solution. So, because she doesn't want Victor to win the game as well. So how can she do that? How can she prove Victor that she actually knows the solution? Any idea? This guy's crazy. Yeah, okay, maybe. So there is a super cool trick. So let's say that Peggy takes a cardboard and she cuts out a shape of Wally on the cardboard. And this cardboard needs to be bigger than the original picture. Then we take the picture, and Peggy is going to overimpose the cardboard over the picture of Wally. In that way, we can see Wally from the other side, but we don't see where exactly in the picture Wally is. So in that way, Victor is convinced that Peggy knows the answer, but he doesn't know how. So this is pretty much the essence of zero-knowledge proof. There is another cool example. So this problem is the three-colorable graph. So we have three colors. We want to color a graph like that. And there is a caveat. We don't want any two neighbors nodes to be of the same color. So we don't want, like, for example, the first one, like the one on the top red, and the one below it shouldn't be red, because they're connected. So let's say this is actually an NPcomplete problem. So it's a little bit complicated to solve. So it's something that you might want to outsource to a different company. So let's say Google found a solution to this problem because they have infinite resource, and they're offering these services. So like I'm Peggy, I'm Victor, I'm not Peggy. So Google is Peggy, and Google wants to prove me that they found a solution to the problem. And of course, if they've managed to find a solution, I will pay them because I need it for my business. I mean, I sell color graphs or whatever. And but there is a problem, because I don't want to send them money before knowing they actually found the solution. It's a very tricky problem. Maybe they didn't really find the solution. Maybe they're cheating. So we are kind of stuck, because I don't want to pay them. They don't want to give me the solution. We're stuck. So what can we do? So the Google engineers devise a game. So they say, okay, that's fine. You don't trust us. We don't trust you. We have a very good business relationship. So let's say that this is your graph that we managed to solve. we are just going to cover all the dots on this graph, and you're going to point at one relation between two dots, and we're going to uncover it and tell you if it's correct or not. So, and I'm like, yeah, okay, fine, but you can be lucky, you can just guess, and you can be lucky as well, right? And then the Google engineers say, yeah, sure, but we can repeat this thing as much as we want. So it can be something like this. And like, the more we run this protocol, the more we iterate on it, the more I'm confident that the Google people actually managed to do something good. And in the end, after enough tries, which can be different depending on the problem you're solving, you can be statistically confident that the prover Peggy actually proves something to you. And if there is a mistake, well, that's going to be cool, because eventually, after a while, we're just going to hit one of the evil nodes. So this is, of course, a little bit laborious, because I need to talk to Google, they need to uncover one relationship, then put everything back together, shuffle everything, because otherwise, the problem is that if I uncover enough nodes, I might actually understand the solution. So what the Google engineers are going to do is that between every game that we're playing, they will shuffle the colors so that I will still be able to see if they solve the coloring problem correctly, but I won't know which color is actually in the correct position. This is, again, very annoying to do. Like, it's just very expensive. So we might actually come up with a different solution, which is, I don't want to interact with you guys all the time. Let's just establish a number, and then you will give me, and that's going to be like a random number that we're going to use to seed the entire interaction. And you guys are just going to provide me all the different steps, starting from that unique random source. So if the source is random enough, we can actually be sure that the interaction hasn't been faked. So it's very important, of course, to agree with Peggy, have this agreement between Peggy and Victor to have a proper source. In this way, I don't need to talk with engineers. They just tell me, yeah, of course, I started with this hash that we agreed on, and or it's an hash of some properties of the problem, for example, and we were able to come up with this solution. So we shuffle things, we reshuffle them, blah, blah, blah. This is the entire list. So with a single string of, probably very long in this case because it's a problem with a lot of possibilities, but with just one single string, just one communication between Peggy and Victor, I can be sure that Peggy knows something. Okay, so we have been talking about zero-knowledge proofs for quite a while now. I'm sure you guys are all experts, and you probably know more than me already, which is not much, actually. I'm not a cryptographer. So there are three properties that are emerging from zero-knowledge proofs. Completeness, which is the fact that Peggy can always convince Victor that she knows the answer. Then there is soundness, which means that if someone is pretending to be Peggy, but she doesn't have the same knowledge, she won't be able to impersonate Peggy. And then there is zero knowledge. This is the trickiest of them all, which is we are not really releasing extra information after every round of our game. So like the Google people were shuffling the colors. In other problems, there can be some other precautions, but we don't need to release information about their problems, because otherwise Victor will learn something, and we don't want Victor to learn. There is a slightly more correct definition for zero-knowledgeness, which is that if a Peggy impersonator could rewind time, Victor won't be able to tell the difference, which pretty much means if I'm a Peggy imposter, but I also have magic skills, I can rewind time, and I get caught, let's say that we are doing again the flow with the three coloring thing. So let's say I get caught, and Victor is catching me, and there's like, oh, there's a mistake here, fix it. You're cheating. So what I can do is rewind time, change the color on those two nodes. I know already that Victor is going to pick those two nodes, so I can just fake it till Victor is confident enough of the solution. So this is again very important because it's telling us that Victor is not able to tell the difference between someone rewinding magically time and someone who actually knows the result. Let's go and see things that are a little bit more concrete, because I'm sure, like, I don't know what your companies are doing, but I'm sure nobody is coloring graphs these days. So let's talk about authentication. What happens when we authenticate on a website? I know the web is shit, we have to send a username, password, so we have a set of things that we need to remember, we send them to the server, then the server is taking the password, well, registration is storing them in a proper way, hopefully. And instead on login, they will check an hash of the password with our password. But again, if the server has been compromised, or if they're not using SSL and there is someone in the network listening, our password is pretty much working in plain text, which is not great, because you might be reusing your password, or I don't know, you just don't want your password to be known. So let's think a solution to this problem using zero-knowledge proofs. So I came up with a few examples, and how many of you knows about public-private key pairs? Okay, that's great. So public and private key pairs are tools that we are using a lot in our daily lives. You're using them for SSH, you're using them to have a GitHub account, you're using them for Git. So, and they're actually very important for zero knowledge as well, because they actually exhibit the same properties. Because in the end, with our public and private key pair, we can sign some data, and we can send it to someone else without sending our private key. And then someone else, just by using our public key, will be able to understand if our signature is correct or not. So this is pretty much how we are safe online. And it's a shame that it doesn't happen for password as well. So what I did was to build a small system. I really focus on the UI. I hope you like it. So this is a very simple system. What's happening in the background is that I'm putting a username, I'm putting a password, and then I'm sending it to the server. And what's happening in the background is that I'm taking my password, I'm using it as a source of randomness, and then I'm generating a private key using only that source of randomness. So a private key, it's a form of encryption that uses problems that are intractable by normal computers. So there are some problems that are too hard for us to solve, like factoring primes, or finding a discrete logarithm, or elliptic curves. There are a lot of funky things that we don't really know how to compute fast. So we can use these problems to protect ourselves and to build well, symmetric and asymmetric encryption system. So what's happening here is that I'm using my password, a password that a user is inserting to generate randomness, and from that I'm generating a unique private key. Now I send it to the server. We can see here that I'm debugging things. I just received a public key. So what I'm doing is that I'm throwing away the private key and storing the public key on the server. Now it's time to log in. I'll try to log in. Of course, I make a mistake because typing password is horrible. And the server is going to tell me, no, you can't log in. This is because the new password that I inserted actually went through the same procedure. It generated a new private key, and the private key doesn't match the public key we have stored. So instead I use the same password. Hope I get it right. Yes, OK. The same private key, the same private and public key are going to be generated on the client side. And then what's going to happen is that I'm going to take a piece of text. The piece of text, it's let me in and the date. So that you can actually use the date to validate that something has not been replayed or something's going to happen later. And then I attach my signature that I generated with my private key. I'm going to post the code if you guys want to look into it. We are probably going to have to skim a lot of it because it's just too much, honestly. So this system is kind of working. I can log in. If I put the wrong password, I can't get in. But can you guys identify a problem? Why wouldn't you use this system in production? I'm going to show you some of the code. Any idea? OK, so the bad idea here is that I'm using a password inserted by a user as a source of randomness. That's really, really bad, because if our source of randomness is not random enough, then an attacker could try to replicate the results we obtained and actually hack our system. So it's still a complex attack to perform, so it's not that easy, but you don't want to do this. There are better ways. a better way, for example, which involves other trade-off, is to actually use a slightly different system. So we're still using key pairs to do that. So well, now I'm going to refresh and we're going to see the new website is much better than this one. Okay. So in this new system, I'm inserting username and password. So what's happening here, it looks the same, but in the background it's doing something different. So I'm storing in local storage my private key. So what's happening here is that I'm encrypting a private key with my password. So I'm generating a completely random private key using good random sources. Then I'm encrypting it using my password, the password that I just inserted. I already forgot it actually. Damn, okay. And then yeah, again, I'm just saving it in local storage, and I'm still sending to the server the public key. So now the server has the public key, my client side has the private key. When I log in, it's just gonna log in pretty much, because I'm gonna decrypt the private key with my password, use the private key to generate a signature as I was doing before, and send it. So the cons of this approach is that I have my private key in the local storage. So if there is an attacker that has access to my computer, or someone, or there's some other attack I can think of that makes the attacker get access to my local storage, then they can brute force my local storage, which is still pretty hard, because again, they have to brute force something that is going to give them another random string of numbers. So it's not going to be that simple for them to understand they actually hit the jackpot and decrypted my key. Okay, so well, yeah, we did that. Yeah, what's wrong with it? So again, there are other tricks that can be used to increase the attack size if you're just sending a password. Things like there are some very complicated systems that use a protocol, so multiple interaction between server and client, and they exchange well, some private and public keys. And the main trick is that they do the same thing we did in local storage, so they encrypt the key, so the attacker won't be able to decrypt it very easily and understand you decrypt something simple. But again, it's not perfect, because nothing is perfect in cryptography. And the other problem we have here is that the distribution of our private key is not going to be random enough. So like an attacker could still try to do some heuristic to understand, oh, I really decrypted the private key now. So we are still kind of vulnerable, not vulnerable, but like there is an attack vector going that way. But again, like luckily we live in 2018, there are people who built some really cool protocols, and there are libraries for these kind of things. So I just suggested to use SRP or SPA key. Haha, I remember that. There are a few libraries that work even in Node, and it's just better to use something existing instead of trying to roll out your own crypto. It's good if you want to learn though, because in that way you see the pitfalls, you see, oh crap, why is this thing not working? Is it because I'm generating the wrong prime numbers? Maybe there is an error somewhere. It's a very fascinating process. Okay, so again, as I was mentioning before, public and private key exhibit zero knowledge, completeness, and soundness. So we can actually call them zero knowledge proof. Now, if I'm wrong, because this is not something that people really talk about, I think it's one of the things that people take for granted in the cryptography world. So if I'm wrong and a cryptographer wants to correct me, feel free to. Again, we can see that yeah, PEG is the only one that can provide a signature to Victor. A PEG imposter can't really produce a signature without the private key. The private key, we are not sending the private key because we are just assigning something. And yeah, it's still zero knowledge, because if I had infinite time, I could probably just try to brute force the signature itself, which will take a long time, but it's possible. Okay, so enough authentication stuff. Do you guys remember the problems from before, the graph coloring thing? I hope there are no startups going in graph coloring things around now. Well, the cool thing about that, it's NPcomplete, which means it's a problem that that we can solve polynomially. So it just takes a long time. but we can test if we solve the problems quite quickly. So the cool thing about this class of problems is that they can all be reduced to a three-coloring graph. So we can pretty much say that given we are able to create a zero-knowledge proof for the three-coloring graph problem, we can also do it for all the other NP-complete problems. And some of these NP-complete problems are actually used to encrypt things. So maybe there is something that we can do there. Maybe there is something useful. OK, so let's keep that in mind. What if I were to tell you that I can give you an encrypted number? So to you, just a string of numbers, and tell you that that string is actually an encrypted number which respects some properties. You tell me it's crazy. How can you do that? I mean, it's encrypted. How can I know that there is something inside? So this is one of the cool things that you can do with zero-knowledge proofs. So we can actually create a proof that an encrypted thing that I'm giving to you, it's actually what you want it to be. So let's say that the number that I'm giving you, represents my account balance. I can guarantee you that it's over 0, for example. And I can do that with zero knowledge without telling you how much I have in my bank account. So this has great implication for privacy and for, well, especially cryptocurrency, let's be honest. So the example I'm going to show you is going to use a crypto system called Palier. He's a French guy. And this Palier crypto system has some very cool properties. So what you can do with this is that you can, it's a public-private key again, and you can encrypt things, and you can sum things while they are encrypted. So let's say you guys are all servers, and I have a problem that I want to solve. I can give you an encrypted number to one of you. I can give an encrypted number to one of you. And then you guys can do whatever you want. You can sum them together. You can do, actually, you can just sum them together with the Palier crypto system. But there are some other crypto systems that let you do other operations, that let you do additions and multiplications. And with addition and multiplications, you can do anything. So once you have these two things, the system is called a fully homomorphic system. And that's pretty much like the holy grail of cryptography, because it's just going to let you compute things without knowing what you're computing, which is quite cool. So Palier crypto system is not fully homomorphic, but is slightly simpler. It's additive homomorphic. So you can add things to it. So I can take two Palier encrypted numbers, sum them together, and then I have the encryption of the result. I can also multiply things by plain text. So I can say, well, I have this number encrypted. I can multiply it by another number. Now I have the multiplication of that number encrypted. So let's see what we're going to do with it. So what I did, just because I couldn't sleep at night, was to implement a paper. So like in the cryptography world, so it sounds very flashy. I know you guys are imagining limousines, champagne, and a lot of fun. But it's actually more like this. So no, I don't expect you to read because it's scary. So you see things like this and you're like, oh, cool. I think that's an omega, maybe, yeah? And so you just get this bunch of equations and you try to make sense of them. And the end result is something like this. I'm not going to go through it. So what it's doing is that we are generating, you don't care about my files, okay? We are generating random keys. So we have a public and private key. We have a set of valid messages here. So the valid messages in this system are 42, 666, 13. Okay, maybe a little bit weird. And this is the message we want to send. So we want to send 43. 43 is not in the valid messages. What we want from the system is to fail because it's not something that the protocol is admitting. Instead, if we were to send 42, then that's okay. You can do that. So this is something that can be used, of course, to build much more complex things. The way it works, it's quite fascinating, somewhere here. So what's happening pretty much is that we are going through all the valid messages. We are generating some set of values and starting from random numbers, and then we are balancing them so that they all agree to a certain sum. So that sum, it's actually the hash of all the admitted values. And that hash, as I was telling you before, it's the kind of agreement between Peggy and Victor to say, yeah, this is our random number, we're going to start from here. So it's very hard for Peggy to create, to bypass this random oracle, because of course you can't really fake the encryption on a set of numbers that is known by both parties. So once you have these numbers and you balance them out so that their sum is some number that we agree on, you just sum the rest of them, and then there is a flow where the verifier Victor is checking if the sum is actually matching. And yeah, I see from the faces I'm just talking Arab. Yeah. No, okay. So yeah, it works, hopefully, because I had some problems before. Okay, so this is false, good, because my message is not in. And now, so if it's gonna get stuck, it happens. I think there is a mistake in the way I'm generating coprimes. So let's see if it works. Oh, yes, it works. I'm not gonna run it again because it could fail. So yeah, sometimes it gets stuck. I think this is a mistake I made somewhere. And sometimes it's returning the wrong number, but it's, you see, what the shit. Okay, sorry, my bad. So yeah, it works the first time. So yeah, the thing is that implementing this algorithm, especially in Node.js, is not as simple as in other languages because you don't have certain guarantees. The libraries are a little bit hit and miss. So, but it worked the first time, so that counts. Okay, I'm just gonna finish it here. There are a few usages of zero-knowledge proofs that are maybe going to affect you in the future. I hope so. One of these examples are cryptocurrencies. So cryptocurrencies, especially privacy-aware one like Monero or Zcash, are using zero-knowledge proof to prove the validity of the transaction. There is a proposal to do something similar for Bitcoin. So instead of having to store, for example, the entire ledger of the transaction, we can just store just the zero-knowledge proof. So that's a huge saving in space. Like, for example, with the latest iteration of zero-knowledge proof that is called the bulletproof. Oh, well, actually, this is not, well, this is just an implementation in Haskell, but whatever. So bulletproofs, with this latest iteration, like they are estimating that they can bring down from 160 gigs of data to 17. So that would be a great improvement that will actually make Bitcoin kind of usable. Maybe if you forget about the transaction fees and everything else, but still, there are a lot of improvements, and hopefully some altcoins eventually are going to pick up the right mixture. The other important thing that zero-knowledge proof can be used for are for hiding information. So let's say I want to tell you that I'm over a certain age, but I don't want to tell you how old I am because, look, it's my business. You can do that with zero-knowledge. It's very powerful. Maybe one day, maybe our children are going to live in the blockchain, and their privacy is going to be intact thanks to the cryptographers that are spending their life on these problems. So that's it. You can find the slides on GitHub, on my website. On my website. And yeah, feel free to ask me anything later on or in the future. Thank you.